Welcome students to the MOOC series of lectures on advanced probability theory. This is lecture number 28. If you remember, in the last class we were discussing weak law of large numbers, which states that if x 1, x 2, x n is a sequence of random variables such that expectation of x I is equal to mu I, which is finite, and variance of x I is equal to sigma square I, then this sequence S n upon n convergence in probability to sigma mu I upon n if variance of sigma x I is such that variance of sigma x I upon n square goes to 0 as n goes to infinity. Here S n is equal to x 1 plus x 2 plus, here S n is equal to x 1 plus x 2 plus x n. So, in essence it says that the average of the n random variables converges in probability to the average of their respective means or expectations under certain condition. Now, if x n is a sequence of IIDs, that is independent and identically distributed random variables, then the condition required for weak law of large numbers to hold is expected value of modulus of x I is finite, and in that case sigma x I is equal to 1 to n divided by n converges in probability to mu, which is the common expectation. In essence, what we are saying that this one condition there, that expected value of mod x I is finite, that takes care of the rather more stringent condition that we need for a general scenario when x 1, x 2, x n are any arbitrary sequence of random variables. So, before we move further, let us consider one example. If x 1, x 2, x n are IID uniform 0 1, then G n, which is the geometric mean of x 1, x 2, x n, converges in probability to a constant C show that the above statement is correct. True, and also determined the value of C. Answer: let yi be minus log of x I. Therefore, probability y I less than equal to y is equal to probability minus of log x less than equal to y is equal to probability log x greater than minus y is equal to probability x greater than e to the power minus y is equal to 1 minus probability x less than equal to e to the power minus y is equal to 1 minus e to the power minus y. This is because x is or x I is uniform 0 1. Therefore, log x belongs to minus infinity to 0, that is minus log x belongs to 0 to infinity, implies y belongs to 0 to infinity. Therefore, together we get that y is distributed as exponential with parameter 1, as this is the CDF of exponential 1. Therefore, y 1, y 2, y n are IID exponential 1. Therefore, expected value of y is equal to 1, which is finite. Therefore, expected value of mod y is equal to 1, since y is a positive random variable. Therefore, weak law of large numbers holds good for y i's, that is sigma y I is equal to 1 to n divided by n converges in probability to 1, that is the common mean, common expectation of the yi's, that is sigma minus log xi upon n converges in probability to 1, implies 1 by n sigma minus log xi converges in probability to 1, implies minus 1 by n sigma log xi converges in probability to 1, implies minus 1 by n log of product of xi I is equal to 1 to n converges in probability to 1, implies minus log of product of xi I is equal to 1 to n to the power 1 by n converges in probability to 1, implies minus log of the geometric mean of x 1, x 2, x n converges in probability to 1, implies log g n converges in probability to minus 1, implies g n converges in probability to e to the power minus 1. Therefore, 1 g n converges in probability to a constant c, to the value of c is 1 upon e. Now, I have used a result at this point. The result is that if x n converges in probability to a constant c, then h of x n converges in probability to h of c if h is continuous. So, this is one result which I have used. So, let me prove it. So, statement: if x n converges in probability to c, then the sequence h of x n converges in probability to h of c when h is continuous. Proof: we need to show that given epsilon and eta greater than 0, however small they are, there exists n naught such that for all n greater than equal to n naught, probability modulus of h x n minus h of c less than epsilon is greater than 1 minus eta. We are given that 1 x n converges in probability to c, and 2 h is continuous. Now, since x n converges in probability to C given delta greater than 0 and eta greater than 0, there exists n1 such that for all n greater than equal to n1, probability modulus of x n minus c less than delta is greater than 1 minus eta. Moreover, since H is continuous given delta greater than 0, there exists epsilon greater than 0 such that whenever modulus of x n minus c is less than delta, modulus of h of x n minus h of c is less than epsilon. So, because h is continuous, we get a neighborhood around C in which we get this outcome, we get this result. Therefore, in above we can see probability modulus of h of x n minus h of c less than epsilon is greater than probability modulus of x n minus c less than delta, because this event implies this event. Therefore, this has a higher probability than this event. Therefore, for all n greater than equal to n naught, let us go back. This is the n naught now I am talking about. Probability modulus of h of x n minus h of c less than epsilon is greater than probability modulus of x n minus c less than delta, which is greater than equal to 1 minus eta. Thus, we get 1 n naught such that this property therefore, the convergence of h of x n in probability to h of c is obtained for all n greater than equal to n naught. Hence, if h is continuous, then we see that x n converging in probability to C implies h of x n converges in probability to h of C. Okay. So, let us now revisit the theorem that we were proving. The theorem was that let x n be any sequence of random variables, let y n be S n minus expected value of S n divided by n when S n is equal to sigma x I is equal to 1 to n, a necessary and sufficient condition for x n to satisfy weak law of large numbers is that expected value of y n square upon 1 plus y n square goes to 0 as n goes to infinity. Note that we already proved in the last class if expected value of y n square upon 1 plus y n square goes to 0 as n goes to infinity, then the sequence of random variables x n satisfies weak law of large numbers. We now prove the converse. Suppose x n satisfies weak law of large numbers, we need to show that expected value of y n square upon 1 plus y n square goes to 0 as n goes to infinity. Proof: expected value of y n square upon 1 plus y n square is equal to integration minus infinity to infinity y square upon 1 plus y square f n y dy, where f n y is the PDF of y n. This we know because we are computing the expectation of a function of a random variable, and we have done this many times before. Therefore, expected value of y n square upon 1 plus y n square is equal to integration over a y square upon 1 plus y square f of f n of y dy plus integration of y square upon 1 plus y square f n y dy on a complement, where A is the set of omega such that modulus of y n omega is greater than epsilon, and therefore, a complement is the set of omega such that modulus of y n omega is less than equal to epsilon. Now, note that y square upon 1 plus y square is less than equal to 1, since y square is greater than equal to 0. Therefore, y square is less than equal to 1 plus y square for all y. Now, we are going to plug in this expression. Therefore, let us rewrite expectation of y n square upon 1 plus y n square is equal to integration over a y square upon 1 plus y square f n y dy plus integration over a complement y square upon 1 plus y square f n y dy. Since this is less than 1, we can write it as this is less than equal to a into 1 f n y dy plus integration over a complement y square into f n y dy. This is because y square is less than 1 plus y square. Therefore, y square upon 1 plus y square is less than y square. Less than equal to probability of A, because if we take 1 out, this gives the probability of A plus integration over A complement epsilon square into f n y dy. This is because A is equal to such that modulus of y n is greater than epsilon. Therefore, on A complement modulus of y n is less than equal to epsilon. Therefore, y n square is less than equal to epsilon square is equal to probability of A plus epsilon square into probability of A complement, because if we take epsilon square out, we get probability of A complement is equal to probability of A plus epsilon square, since probability of A complement is less than equal to 1. Therefore, y n square upon 1 plus y n square is less than equal to probability of A plus epsilon square is equal to probability modulus of y n greater than epsilon plus epsilon square. Now, y n is equal to S n minus expected value of S n divided by n is equal to sigma x I is equal to 1 to n minus expected value of sigma x I is equal to 1 to n divided by n, and we are given that x I satisfies weak law of large numbers. Therefore, probability modulus of sigma x I minus sigma mu y divided by n greater than epsilon converges in probability to 0 as n goes to infinity, where mu y is equal to expected value of x I. Therefore, from this result and this result, we get that the value of y n square upon 1 plus y n square can be made arbitrarily small as n goes to infinity. Since epsilon can be taken arbitrarily small positive quantity. Therefore, we get expected value of y n square upon 1 plus y n square goes to 0 as n goes to infinity. Proved. Now, let us consider a stronger version of law of large numbers, which is called strong law of large numbers or SLLN. So, statement: a sequence of random variables x n is said to obey strong law of large numbers with respect to a sequence of constants B n, where B n goes to infinity as n goes to infinity if S n minus n upon B n converges almost surely to 0. That is probability of A, where A is equal to the set of omega on which S n upon B n is equal to n upon B n is equal to 1. That means, the measure of the set on which S n upon B n equals A n upon B n, that has the probability 1. Note, the n's are called centering constants and the Bn's are called norming constant. In a general form, of weak law of large numbers, we can use this sequence of numbers n's and the sequence of numbers bn's such that bn is going to infinity as n goes to infinity, and we say that xn obeys weak law of large numbers with respect to the sequence Bn of constants if there exists a sequence n of real numbers such that Sn minus an upon Bn converges in probability to 0 as n goes to infinity. Note that this is a general form of weak law of large numbers. In general, we consider n is equal to sigma over mu I and Bn is equal to n, and put these values here, you will get that we have defined weak law of large numbers in this general form with this particular value of a n and b n. Note, if x 1, x 2, x n are IID random variables, then sigma x I upon n converges almost surely to mu. So, these results can be proved with some more knowledge of mathematics and measure theory, but that is not within the gamut of this course. So, I am not proving this result. So, let us take these results, and I stop this lecture by stating a few more important results on law of large numbers. One, if x 1, x 2 are IID random variables such that probability modulus of x n is less than equal to k is equal to 1 for some positive constant k, then Sn upon n converges almost surely to mu, where mu is the common expectation. Two, if x1, x2 etc. is a sequence of independent random variables, then x n converges almost surely to 0 implies and implied by sigma I is equal to 1 to infinity probability modulus of x I greater than epsilon is finite for all epsilon greater than 0. It is very easy to visualize, as the probability that x n is taking the value 0 is going to 1. Therefore, whatever positive epsilon we take, the modulus, the absolute value of x I to be greater than that has to be finite, because if that is infinite, then x n cannot converge to 0 with probability 1. 3. This is called Kolmogorov inequality. Which states that if x 1, x 2, x n is a finite number of independent random variables, with common expectation is equal to 0, and if the variance of x I is equal to sigma square I, then for any epsilon greater than 0, probability maximum over 1 less than equal to I less than equal to n modulus of S I greater than epsilon is less than sigma summation of sigma I square I is equal to 1 to n divided by epsilon square. 4. If x 1, x 2 etc. x n is a sequence of random variables such that sigma variance of x I is equal to 1 to infinity is finite, then sigma I is equal to 1 to infinity x I minus expected value of x I converges almost surely to 0. A corollary to the above is that if x n is a sequence of independent random variables and if sigma variance of x k upon b k square k is equal to 1 to infinity is finite, and Bk goes to infinity as k goes to infinity, then Sn minus expected value of Sn divided by Bn converges almost surely to 0. 5. Borel's strong law of large numbers. For a sequence of Bernoulli trials, with constant probability of success, P, the strong law of large number holds with A n is equal to n p and B n is equal to n, that is sigma x I upon n converges almost surely to P. Number 6, Poisson's weak law of large numbers, also on Bernoulli trials, but here P is not a constant, rather it can change for each x k such that x k takes the value 1 with probability k and 0 with 1 minus p k, 1 with probability p k and 0 with 1 minus p k, then sigma x I upon n converges in probability to sigma p I upon n. And finally, Kolmogorov's strong law of large numbers, which state that if x n is a sequence of IID random variables, then Sn upon n converges almost surely to the common mean mu implies and implied by expected value of modulus of x I is finite. Note that this is the same for all I. Okay friends, I stop here today. So, I have given you a lot of results concerning convergence of sequence of random variables when the number of such variables is large, and there are several theorems stating different results. They can be proved mathematically using measure theory and analysis, but as I said that in this course we are not going into the details of those proofs, but it is better for our applications to remember these results. With that, I conclude my talk on law of large numbers. From the next class, we shall start the most fundamental result of probability, or one of the most fundamental results of probability, namely central limit theorems. Okay friends, thank you.